Hey, welcome back to Math with Patrick and Quill. Today is December 20th, and we're solving problem 354 from the Daily Epsilon calendar. And the answer today, x should be 20 because that's today's date. We have some kind of geometry looking diagram today. I think it's safe to assume that we have a rectangle, and then inside the rectangle we have two semicircles that are tangent to each other or that touch at exactly one point. And we have a length right here. It's kind of complicated. 5 times the square root of 6 minus 5 times the square root of 2. But hopefully we can use this length and then some of the rules in the diagram to learn what the length of x is here. I think for starters, I'm just going to rename this as a variable a because I want to strike a relationship between x and the number that we have, and I'd rather not write all this out every single time. Another thing that I know is useful for these types of geometry diagrams is that anytime you have a circle, it's pretty useful to just redraw more radii in the diagram and see if it's helpful at all. And I'm noticing something kind of cool here where these two radii in both of our semicircles attach to each other right there. This tick mark and that tick mark show me that the radius in both of the circles are the same. And all of these are going to be that length a. There is like a little bit of overlap here, right? Like I can't just say that this length all the way down is 4a, like 1, 2, 3, 4, just because there is this little overlap in the middle. Something useful to investigate is what's happening with this middle diagonal, and I think we can say that there's like a 30-degree angle right here. And my reasoning is that when you stack circles on each other, and pardon these not actually being circles, there's two ways that they stack. Either you could just have circles stacked like this, in which case we would make a perfect square. All of these would join up at 90-degree angles. And the other way we could do it is what's in this diagram when we have three different circles that are cotangent to each other, I guess. I don't know if I'm using that word right here, but they're all tangent to each other. They're all supposed to be intersecting at just one point. And if we connect these centers to each other, we're going to get an equilateral triangle. My reasoning is that all of these are the same radius. We can assume that when we're stacking all these circles, all the radii are the same. And then if we're trying to connect one to the other, we're just going directly towards the other point. And so all of these are going to be straight lines. So overall, when we have these stacked circles, we know they're going to connect in equilateral triangles, or at least their centers are going to connect in equilateral triangles. So that's why I'm pretty confident that we have a 30-degree angle here. Last connection here is that the whole rectangle has a diagonal of x, and so to find the length of x, we're just going to eventually do some kind of Pythagorean theorem. Here's the first thing I'll actually write to try to solve it. To do the Pythagorean theorem here, we'd say that the square of the hypotenuse is equal to both of the legs summed after squaring. And this a actually is going to be the same value a right here. We know this because we can translate the length of a over there. So I will keep this variable. But b is going to be the longer leg, and I don't really want to use more variables if I don't have to. So I'm hoping I can find some expression in terms of a for the longer side. For starters, we can see that this length here is already a, as is this one down here. And the only thing we're missing is that middle portion, which I'll color code and say green. So we could either find the length of this side or that side, and we would find the last missing piece of our longer leg. I think I'll just take a look at the bottom part, just because they're going to be the same, so we might as well pick one. We have I think this is a 30, 60, 90 triangle, right? I already decided that this angle right here is 30, so equivalently, this one could have been 30 as well. Here is the side A, and these triangles have a proportional relationship that you could prove with the Pythagorean theorem, that if the short leg is 1, then the longer leg is root 3, and the hypotenuse is 2. And I am going to use this relationship to find some kind of expression for the longer leg, because that's the same thing as this green distance right here. That's just going to be a times root 3. So to find the whole length, I could just do a plus a times root 3 plus another a. That could look like 2a plus root 3 times a. And maybe I'll factor out the a in my final expression. So I'll call it 2 plus root 3 times a. And that's going to be the whole length of the longer side. Now to isolate x, all I need to do is square root both sides. So now I have some kind of answer. And hopefully, after plugging in the actual value for a, I do get 20 for today. So let's just try it out, I guess. The left a squared seems a little bit more appealing to try than this one right here because there's more multiplication that I need to do on the right side. But squaring this doesn't seem fun either. Oh well, I guess I'll try. So we'll have the square root of, and then when I square a binomial, I'll have the square of the first, which is going to be 5 times root 6 times root 6. Both of these collect up to just be the number 6. This is a 25, and so now we get the number 150. Then we're going to get minus twice the product of both of these, minus because there was already a minus sign there. The product of those is going to be 5 times root 6 times root 2. That's going to be 25 root 12. I could simplify that root 12. I think for now, I'm just going to choose not to. But I will combine that times 2 with a 25, and I'll call this 50 times root 12. And to finish off squaring this term, I will square the last one. So that's going to be 5 times root 2, which is 25 times 2, which is 50. So we're going to get a plus 50 at the end. Now for the next one, I think what I'll do first is distribute this 2 plus root 3 with my other term here. Maybe I'll factor out the 5 and deal with it later. So I don't need to worry about that 5 as I'm distributing everything. And then I will then have to square this value later. So first times the first is 2 root 6. These two together gives me a minus 2 root 2. Then we get plus root 18. And then finally minus root 6. And then all of this will be squared and also multiplied by 5. Maybe let's call that a 25 because I guess I could distribute that square in. And we could simplify this one a touch, right? This 2 root 6 minus the root 6 at the end. Both of these could combine together. And then can I simplify root 18? I mean, I can. This is root 9 times root 2. So, it's 3 root 2. There we go. And I have another root 2 term right here. So if I have minus 2 root 2 plus 3 root 2, that is just plus 1 root 2. So I can erase these and make this a plus sign. That's convenient. And yeah, interestingly, it's this guy again, but with a plus sign in the middle. That's kind of cool. I could square this fairly easily. Square of the first, square of the last, and then plus twice the product of both. And then finally, I have a 25 at the front. So this is now going to be all of this squared. So I'll write that in. Plus 25 times, why not, let's call it 8 plus 2 root 12. Let's collect up our like terms. We have just some numbers in here, right? 150 plus 50, that's going to be 200. And then plus 25 times 8, that's another 200. So we have 400. And then now we have some radical numbers to deal with. I think these should cancel out. We have minus 50 root 12. And then once we distribute this, we have plus 50 root 12. Great. So those do cancel out, and I don't need to worry about those radical terms underneath my square root sign. That's good because I don't really want to think about how to take the square root of another sum with a square root in it. And now that we have x is equal to the square root of 400, well, that is just 20, and we're all done. So x is exactly 20. That is this long diagonal in the geometry diagram, and we can find it by just knowing the length of this part right here. So I'm all done. Thank you for watching, and I'll see you tomorrow. Bye.